rotation, arbitrary rigid body dynamics, interaction to arbitrary angular momentum and MIS, moment of inertia, NL of Newton law of motion, rolling and collision. A rigid body. When the distance between any 2 points in the body remains always constant, even after applying very large force, it is known as a rigid body. The rigid body is supposed to be composed of several identical bodies having masses distributed throughout the rigid body. For analysis purposes, in this case, we introduce the concept of center of mass. Center of mass, it is defined as the point lying inside or outside the rigid body at which the total mass of the body is supposed to be concentrated. Mathematically, it is defined as the mean distance from a reference axis considered at which the total mass is concentrated. That is RCM equals to M1 R1 vector plus M2 R2 vector plus Mn Rn vector divided by M1 plus M2 plus M3 In projection form, XCM equals to M1 X1 plus M2 X2 plus Mn Xn divided by M1 plus M2 plus Mn equals to sigma mi xi I equals to 1 to n divided by sigma I equals to 1 to n mi. Similarly, YCM equal to sigma I equals to n mi yi divided by sigma mi, and ZCM equals to sigma mi zi divided by sigma I equals to n mi. Now, velocity of center of mass. It is the rate of change of the position of the center of mass with respect to time. That is VCM equal to dy dt RCM. This implies VCM vector equals to M1 dr1 vector by dt plus plus Mn drn by dt divided by M1 plus M2 plus Mn equals to M1 V1 plus M2 V2 plus Mn Vn divided by M1 plus M2 plus Mn. Again, in projection for VCMX, that is center of mass along x-axis, M1 V1 x plus M2 V2 x plus Mn Vn x divided by M1 plus M2 plus Mn. VCMY equals to M1 V1 y plus M2 V2 y plus Mn V1 y divided by M, because sigma M1 plus M2 M2 is equal to M. And VCMZ equals to M1 V1 Z plus M2 V2 Z plus Mn Vn Z divided by M. Also, VCM equals to M1 V1 vector plus M2 V2 vector plus M plus Mn Vn divided by M1 plus M2 plus Mn, or M into VCM equals to M1 V1 plus M2 V2 plus M3 V3 Mn Vn equals to P1 vector plus P2 vector plus P3 vector plus Pn vector. That is sum of all the momentum. Or this implies sigma P equals to M into VCM. That is sum of all momenta is equal to the mass of the system and velocity of center of mass. Acceleration of center of mass. It is the rate of change of the velocity of center of mass with respect to time. Mathematically, it is given by ACM equals to dy dt VCM equals to M1 dV1 by dt plus M2 V2 by dt M2 into dV2 by dt plus Mn into dVn by dt divided by M1 plus M2 plus Mn. This implies ACM vector equals to M1 A1 vector plus M2 A2 vector plus Mn vector divided by M1 plus M2 plus Mn. ACM vector equals to M1 A1 vector plus M2 A2 vector plus Mn divided by M. Again, in projection form, that is acceleration of center of mass along x-axis, that is M1 A1 x plus M2 A2 x plus Mn1 An x divided by M. ACM y equals to M1 A1 y plus M2 A2 y plus Mn An y divided by M. ACM Z M1 A1 Z plus M2 A2 Z plus Mn Nn Z divided by M. Also we have ACM equals to M1 A1 plus M2 A2 vector plus Mn A divided by M. So M into ACM vector equals to M1 A1 vector plus M2 A2 vector plus Mn N vector equals to F1 vector plus F2 vector plus F3 vector plus Fn vector. Hence sigma F vector equal to M into ACM vector. That is resultant of total force, individual force is equal to the mass of the body and acceleration of the center of mass. Method of finding position of the center of mass. Mass moment method. Second area method. Area moment method. And third integration method. Fourth method of symmetry. First explanation of mass moment method. In this case, we find the moment of the masses of the different particles and then the mean value of calculated. That is RCM equal to sigma MIRI vector divided by sigma IMI. Also YCM equals to sigma MI XCM equal to sigma MI XI divided by sigma MI, and YCM sigma MY Y divided by sigma MI. ZCM sigma MI ZI by sigma MI. Example of figure. So locate the center of mass and prove that it is independent of the frame of reference considered. There are two bodies placed at a distance of L. This is M1 and this is M2. M1 is placed at the origin and M2 is placed at a distance L. There will be at any point between these a center of mass. Now XM, we know that M1 x1 plus M2 x2 divided by M1 plus M2, because it is origin, so x coordinate is 0 and the M2 L coordinate is L. So M2 L by M1 plus M2, and this is the center of mass at a distance M2 L by M1 plus M2. Method 2, when reference point is placed at this point, that is origin at fixed at mass M2, then center of mass XM will be M1 into minus of L1 because it is in this direction, so distance is minus L1 plus M2 into 0 because x coordinate 0 divided by M1 equals to minus M1 L by M1. Negative sign shows that this is in the this side. Third, when the body is placed in the xy plane, then x equal to m1 x1 plus m2 x2 by m1 plus m2 m1 x1, this because its x coordinate is x1 plus m2 into this x coordinate is x2 x1 plus l, so m2 into x1 plus l divided by m1 plus m equals to x1 plus m2 into l by m1 plus m2. And YCM equal to m1 y1 plus m2 y2 by m1 plus m2, because y coordinate is same y1 for both bodies. This also y coordinate is y1, so y2 will be y1 and m1 plus m2 will be common, so m1 plus m1 by m2 will cancel out, becomes YCM equals to y1. From figure, find the center of mass of different figure as shown in the figure and calculate and solve this. Area moment method. It is another form of mass moment method. In this case, we fix the moment of area of segments and then the mean value. Mathematically, we have m equals to a into t into rho, where density is the rho is density, t is the thickness, a is the area, mass is area into thickness, that is volume, and this will give density. The volume into density is mass. So xcm equals to a1 t1 rho 1 into x1 plus a2 t2 rho t into x2 plus an tn rho n into xn divided by a1 t1 plus rho 1 plus a2 t2 by rho 2 plus an tn plus rho n. This represents mass m1, m2, m2, m3, and this is representing m1 into x1, m2 into x2. Now ycm is a1 t1 rho 1 into y1 plus a2 t2 rho 2 into y3 plus that n t in yn and divided by n t1 a1 plus a2 t2 rho 2 plus that n tn rho n. If the thickness and the density of the body remains same, then xcm equals to a1 x1 plus a2 x2, thickness and density, okay, plus an xcm divided by xn divided by n plus a2 plus that n. Similarly, ycm equals to a1 yn plus a2 y2 plus that n yn divided by a1 plus a2 plus that n. Locate center of mass. Here a1, this is a1 equal to 1200, it is equal to 300 and 3 equal to 300. xcm की 1200 into 5 plus 300 into 25 into 2 divided by 1800 equal to 1200 into 60 plus 300 115 plus 355 by 1800. Answer. Locate the center of mass. Now method of integration. It is used for the continuously distributed masses in the rigid body. It is the mass moment method in the elementary form. In this case, xcm integration xdm by integration dm and ycm integration ydm by integration dm and zcm integration zdm by integration dm. So xcm integration xdm by integration dm. For example, this is a ring of shown as it is placed vertically on the surface, not vertically in any direction, plane, maybe plane. X position will be its x equal to if this is theta, then this is r cos theta and this is r sin theta. So r cos theta integration m by pi r into r d theta, okay, integration 0 to pi m by pi r into r d theta, or r into 0 to pi cos theta d theta by 0 to pi d theta, r into sin theta 0 to pi theta equal to r into theta by pi equal to 0. And ycm is integration ydm by integration dm 0 to pi r sin theta m by pi r into r d theta, integration of m by pi r 0 to pi r d theta, m by pi r cancel out. So we have r into, now integration sin theta theta minus of cos theta 0 to pi by pi, or minus of r cos pi minus cos 0, minus of cos pi equal to minus 1 or minus 1 minus r, so minus 2r over pi. So center of mass equals to 0 comma 2 pi.